Hello everyone, and welcome back to the introductory module on organic chemistry. In the previous lecture, we explored the connections between organic chemistry and our daily lives. Today, our focus shifts to the pivotal role organic chemistry plays in various industries. The previous lecture concluded by detailing the role of vitamin C in our diet. Vitamin C is manufactured on a huge scale by Roche, a Swiss company. All over the world, there are chemistry-based companies making organic molecules on scales varying from a few kilograms to thousands of tons per year. This is good news for students of organic chemistry. Knowing how molecules behave and how to make them is a skill in demand, and it is an international job market. The petrochemicals industry consumes huge amounts of crude oil. The largest refinery in the world, in Jamnagar, India, processes 200 million liters of crude oil every day. An alarmingly large proportion of this is still just burned as fuel, but some of it is purified or converted into organic compounds for use in the rest of the chemical industry. Some simple compounds are made both from oil and from plants. The ethanol used as a starting material to make other compounds in industry is largely made by the catalytic hydration of ethylene from oil. But ethanol is also used as a fuel, particularly in Brazil, where it is made by fermentation of sugarcane. Biodiesel is made in a similar way from the fatty acid components of plant oils. Plants are extremely powerful organic chemical factories, with sugarcane being among the most efficient of all of them. Photosynthesis extracts carbon dioxide directly from the air and uses solar energy to reduce it to form less oxygen-rich organic compounds from which energy can be re-extracted by combustion. Plastics and polymers take much of the production of the petrochemical industry in the form of monomers such as styrene, acrylates, and vinyl chloride. The products of this enormous industry are everything made of plastic, including solid plastics for household goods and furniture, fibers for clothes, elastic polymers for car tires, light bubble-filled polymers for packing, and so on. Worldwide, 100 million tons of polymers are made per year, and polyvinyl chloride manufacture alone employs over 50,000 people to make over 20 million tons per year. Many adhesives work by polymerization of monomers, which can be applied as a simple solution. You can glue almost anything with superglue, a polymer of methyl cyanoacrylate. Washing up bowls are made of the polymer polyethylene, but the detergent you put in them belongs to another branch of the chemical industry. Companies like Unilever, Procter & Gamble produce detergents, cleaners, bleaches, and polishes, along with soaps, gels, cosmetics, and shaving foams. These products may smell of lemon, lavender, or sandalwood, but they too mostly come from the oil industry. Products of this kind tend to underplay their petrochemical origins and claim affinity with the perceived freshness and cleanliness of the natural world. They also try to tell us, after a fashion, what they contain. Try this example. The list of contents from a well-known brand of shower gel, which we are reassuringly told is packed with natural stuff, including 10 real lemons, and contains 100% pure and natural lemon and tea tree essential oils. The particular detergents, surfactants, acids, viscosity controllers, and so on are chosen to blend together to give a smooth gel. The result should feel, smell, and look attractive and work as an effective detergent and shampoo. In this sense, the yellow color and lemon scent are considered fresh and clean by the customer. Notably, several of the ingredients are added as pure compounds. The ones which are not are mixtures of isomers or polymers. The most impure ingredients are the mixtures of hydrocarbons referred to as the pure and natural essential oils. So, is it packed with natural stuff? Indeed, it is. It all comes from natural sources, the principal one being decomposed carboniferous forests trapped for millions of years underground. I certainly hope this course will set you on the path of understanding the sense and the nonsense of this sort of thing. The coloration of manufactured goods is a huge business, with a range of intense colors required for dyeing cloth, coloring plastic and paper, painting walls, and so on. One of the most commonly used dyestuffs is indigo, an ancient dye that used to be isolated from plants but is now made from petrochemical feedstocks. It is the color of blue jeans. More modern dyestuffs can be represented by benzodipheronones, phthalocyanine metal complexes, and diketoparolopyrols, often abbreviated as DPPs. The benzodipheronones, developed by ICI, are used for coloring synthetic fabrics such as polyesters. Phthalocyanine metal complexes typically produce blue or green hues, while the high-performance pigments from the DPP series, developed by Ciba-Geigy, are red. The scent of the shower gel mentioned earlier came from a mixture of plant extracts, with the key ingredient being citral. Major fragrance and flavoring companies handle both natural and synthetic ingredients. Naturals are mixtures of compounds extracted from plants. Synthetics are single compounds, sometimes present in plant-derived sources and sometimes newly designed molecules, which are mixed with each other and with natural compounds to create a scent. A typical perfume will contain 5 to 10% fragrance molecules in an ethanol water mixture. So, the perfumery industry needs a very large amount of ethanol and, you might think, not much perfumery material. In fact, important fragrances like jasmine are produced on a 10,000 tons per annum scale. The cost of a pure perfume ingredient like cisjasmone, the main ingredient of jasmine, may be several £100, dollars, or euros per gram. Chemists produce synthetic flavorings such as smoky bacon and even chocolate. Meaty flavors come from simple heterocycles such as alkyl pyrazines present in coffee as well as roast meat, and furanol, originally found in pineapples. Compounds such as corylone and maltol give caramel and meaty flavors. Mixtures of these and other synthetic compounds can be tuned to taste like mini roasted foods from fresh bread to coffee and barbecued meat. Some flavoring compounds are also perfumes and may also be used as an intermediate in making other compounds. Vanillin is the main component of the flavor of vanilla but is manufactured on a large scale for many other uses too. Food chemistry includes much larger scale items than flavors. Sweeteners such as sugar itself are isolated from plants on an enormous scale. You saw sucrose earlier, but other sweeteners such as saccharin and aspartame are made on a sizable scale. Aspartame is a compound of 2 of the natural amino acids present in all living things, and over 10,000 tons per annum are made by the NutraSweet company. One of the great revolutions of modern life has been the expectation that humans will survive diseases because of a specifically designed treatment. In the developed world, people live to old age because infections which used to kill can now be cured or kept at bay. Antibiotics are our defense against bacteria, preventing them from multiplying. One of the most successful of these is amoxicillin, which was developed by SmithKline. The 4-membered ring at the heart of the molecule is the beta-lactam, which targets the disease-causing bacteria. Medicinal chemists also protect us from the insidious threat of viruses which use the body's own biochemistry to replicate. Tamiflu is a line of defense against the ever-present danger of a flu epidemic, while ritonavir is one of the most advanced drugs designed to prevent replication of HIV and to slow down or prevent the onset of AIDS. The best-selling current drugs are largely designed to address the human body's own failings. Sales of Lipitor and Nexium both topped $1.3 billion in 2022, figures which serve to illustrate the financial scale of developing safe and effective new treatments. Lipitor is one of the class of drugs known as statins, widely prescribed to control cholesterol levels in older people. Nexium is a proton pump inhibitor, which works to reduce peptic and duodenal ulcers. We cannot maintain our present high density of population in the developed world, nor deal with malnutrition in the developing world unless we preserve our food supply from attacks by insects and fungi and from competition by weeds. The world market for agrochemicals produced by multinationals such as Bayer CropScience and Syngenta is over $15 billion per annum divided between herbicides, fungicides, and insecticides. Many of the early agrochemicals were phased out as they were persistent environmental pollutants. Modern agrochemicals have to pass stringent environmental safety tests. The most famous modern insecticides are based on the plant-derived pyrethrins, modified chemically to stabilize them against degradation in sunlight, as demonstrated in decamethrin by the brown and green portions. Decamethrin has a safety profile that is 10,000 times safer for mustard beetles than for mammals, can be applied at a rate of only 10 grams per hectare, and leaves no significant environmental residue. As you learn more chemistry, you will appreciate how remarkable it is that nature should produce the three-membered rings in these compounds, and that chemists should use them in bulk compounds to be sprayed on crops and fields. Even more remarkable in some ways are the fungicides based on a five-membered ring containing three nitrogen atoms, the triazole ring. These compounds inhibit an enzyme present in fungi but not in plants or animals. Fungal diseases are a real threat. As in the Irish potato famine of the 19th century, the various fungal blights, blotches, rots, rusts, smuts, and mildews can overwhelm any crop in a short time. All the compounds I have shown you are built up on hydrocarbon skeletons. Most have oxygen or nitrogen as well. Some have sulfur and some phosphorus, and maybe the halogens. These are the main elements of organic chemistry. But organic chemistry has also benefited from the exploration of the rest of the periodic table. The organic chemistry of silicon, boron, lithium, tin, copper, zinc, and palladium has been particularly well studied, and these elements are common constituents of organic reagents used in the laboratory. You will meet many of them throughout this course. Butyllithium, trimethylsilyl chloride, tributyltin hydride, diethyl zinc, and lithium dimethylcuprate provide examples. The halogens also appear in many life-saving drugs. Antiviral compounds such as phyluridine, which contains both fluorine and iodine, as well as nitrogen and oxygen, are essential for the fight against HIV and AIDS. They are modeled on natural compounds from nucleic acids. The naturally occurring cytotoxic and anti-tumor agent halomon, extracted from red algae, contains bromine and chlorine. The organic chemist periodic table would have to emphasize all of these elements and more. New connections are being added all the time. Before the end of the last century, the organic chemistry of ruthenium, gold, and samarium was negligible. Now reagents and catalysts incorporating these metals drive a wide range of important reactions. So where does inorganic chemistry end and organic chemistry begin? Would you say that the antiviral compound phosgornate was organic? It is a compound of carbon with the formula CpO5 sodium 3, but it has no CH bonds. And what about the important reagent tetroxys triphenylphosphine palladium? It has lots of hydrocarbon, 12 benzene rings in fact, but the benzene rings are all joined to phosphorus atoms that are arranged in a square around the central palladium atom. So the molecule is held together by carbon-phosphorus and phosphorus-palladium bonds, not by a hydrocarbon skeleton. Although it has the very organic-looking formula, C72, H60, P4, palladium, many people would say it is inorganic. But is it? The answer is that we don't know, and we don't care. Strict boundaries between traditional disciplines are undesirable and meaningless. Chemistry continues across the old boundaries between organic chemistry and inorganic chemistry, organic chemistry and physical chemistry or materials, or organic chemistry and biochemistry. Be glad that the boundaries are indistinct, as that means the chemistry is all the richer. These lovely molecules belong to chemistry. To sum it up, I have told you about organic chemistry's history, the types of compounds it concerns itself with, the things it makes, and the elements it uses. Organic chemistry today is the study of the structure and reactions of compounds in nature, of compounds in the fossil reserves such as coal and oil, and of those compounds that can be made from them. Organic compounds will usually be constructed with a hydrocarbon framework, but will also often have atoms such as oxygen, nitrogen, sulfur, phosphorus, silicon, boron, halogens, and metals attached to them. Organic chemistry is used in the making of plastics, paints, dyestuffs, clothes, foodstuffs, human and veterinary medicines, agrochemicals, and many other things. This course is about all the things described here. It is about the structures of organic molecules and the reasons behind those structures. It is about the shapes of organic molecules and how the shape relates to their function, especially in the context of biology. It explains how organic structures and shapes are discovered. It tells you about the reactions the molecules undergo and, more importantly, how and why they behave in the way they do. It tells you about nature and about industry. It tells you how molecules are made and how you too can think about making molecules. This is the landscape through which you are about to travel. And, as with any journey to somewhere new, exciting, and sometimes challenging, the first thing is to make sure you have at least some knowledge of the local language. Fortunately, the language of organic chemistry could not be simpler. It is all pictures. The following lectures will get us communicating. Thank you for your attention.